Look at that lag.
Yeah, I was gonna say, some of you move slower.
You can totally do the wave right now. It's perfect.
This is amazing.
Hilarious. Let's just do this all class.
That was entertaining.
You guys, I've had way too much fun today because I have a student who's getting the robotics lab set up with some of the new robots that we got. And I was driving around this robot, and today I was sitting in the robotics lab driving it around, and people were walking by, and stopping and turning it towards them. Yeah. So I've been having a lot of fun. Whew, okay. Well, that made my day. So this is sort of hopefully going to wrap up the theory and bring us to like the current state of, I don't know, maybe how people like to think about measurement from a philosophical perspective, I guess you could say. And this we're going to put under the heading of the Epistemology of Measurement. The hot dogs today were excellent. However, burping them is not as good. It's like
Are we saying like Costco hot dog or?
no at the thing happenings thing.
Well, you went back and got another one without a bun, man.
I did.
Yeah. I mean, come on.
You noticed that?
I was so proud of me.
Well, he was trying to be sneaky, and like he was eating, and then he like walked around, and then no bun, just the hot dog.
That's right.
He's only knew that because he's sitting next to me and you actually paid attention.
Apparently, you know,
I watch everything.
yeah, just gotta
The
watch
government,
out.
Man, I told you.
You are the government?
So, epistemology, as I'm sure you all know, is the study of knowledge and how it is acquired. Epistemology of measurement is the study of how knowledge is acquired through measurement. Kind of makes sense, right? The model-based description of measurement above is closely associated with the study, and I kind of explained how last time model-based measurements is kind of how a lot of people think about it now. It's one of the main, I guess, schools of measurement theory. One of the most interesting aspects of this work is the way it both questions the validity of and offers an alternative to the intuitive realism about measurement that suggests that there is a real quantity independent of the measurement and that measurement error is the difference between that quantity and the estimate of the quantity. And remember last time I was like, you know how realism definitely feels like maybe the best of these, probably because I was very biased as I was writing it. But also because it's better. I'm also going to question that a little bit in this section here. And so I think there are a few ways that we can assault realism, which is unnecessarily violent, to put it that way. But it was fun. So the first section I'm calling the Unknowable Real. So this is the first assault on realism that I'm going to give you guys. The exact real value of a quantity cannot be known, at least for continuous scales. That's actually accepted by most people. Okay, you can't know what the real quantity is, but there is one, is what realism is going to say. But we can't know it. This is generally accepted. Therefore, the error between the measurement and the real value can't be known. We are left to compare inherently inaccurate measurements with each other using statistical techniques. Even if measurements are made with different techniques and averaged, we cannot know all these techniques don't share a common systematic error, right? So like we could take a bunch of measurements, and just because they're all close to each other doesn't mean that they're not all wrong, right? If there is some real true value, we can't know what it is, and therefore we can't know what the error is of what we measure because we don't know what the real value is. So that's sort of like putting a little bit of a maybe. I guess it's sort of a hole in the realism perspective. It's like, oh yes, there's a real value, but like we can't know it. So like.
So it's like saying that 12.5 inches is the same as 12.51, or that kind of thing. Or?
Well, it's saying that if there is a real length of, say, so you're saying something's 12.5 inches, so we're trying to measure something, and we say we measure it, we get 12.5, and we get 12.51. We don't know that, like, the real value is not 46. Like, we could, all of our measurements could be off if there's some unknowable real value. There's no reason, there's no way for us to investigate if we're off or not, because we can't know what the real one is.
So what you're saying is all measurements are correct?
I'm not saying that. I'm saying that.
The boys at Bowen would probably disagree with you.
Accuracy versus precision.
So that we're going to talk about that actually.
All
So it's coming right up.
measurements are approximations.
Yeah.
Yeah. So I think we can agree that we never can measure the value exactly and know for sure that we did it. And I think that what I'm trying to introduce here is an acknowledgement of the fact that we could be wrong, but we have a best estimate based on the measurements that we've made.
So essentially, you never say the word exact.
I mean, that's one way to go. Yeah. I mean,
Close enough.
yeah. I mean, that is roughly what we're doing here. It's recognizing the limitations of our measurement abilities, I guess. So then here's the next one. Circles are a thing. Another assault on realism can be made by emphasizing the fact that when measurements take place, some sort of idealizing model of the concrete situation is implicit. This one's a little less obvious, I think. For instance, what would it mean to measure, just one is all we need. What would it mean to measure the temperature of an object without an idealized model of temperature making fluid volumes expand? Okay? Okay, instead, could we start from the theoretical model? So we've got this idea that temperature is how much a fluid expands when we subject it to thermal energy, right? That's what temperature is kind of defined as in a lot of cases. And so then, how could we come up with a measurement for temperature unless we had some sort of idealized model for what temperature meant? So then the question is, instead, could we start from the theoretical model? If we were going to do that, what would temperature even mean? So you've got this sort of theoretical model of what it is you're doing, like measuring temperature, embedded in the measurement that you're taking. And that's okay, but I think that it makes us recognize that we're kind of engaging in some sort of a fiction here when we take a measurement. We're saying temperature is this, and then we measure that, and it's not surprising that we found what we looked for. We had an idea of what it would be, and that's what it was. So there's sort of this circularity there, but it's not what they call a vicious circle. So they call it a non-vicious circle when considered from a historical point of view, which we will now consider. So I did want to take a note here that conventionalists tried to take a way out of the circle by attempting to arbitrarily fix meaning with coordinative definitions, which we talked about. The historical point of view questions the validity of this given the fact that definitions seem to require revision upon the development of sufficiently accurate measurements. That is, the definition of a quantity cannot remain static. So you could define temperature to be how much a fluid expands when subjected to thermal energy. You could define length to be the length of a certain bar in Paris. And that's okay, but I think that when you look at it from a historical point of view, you see that we revise our definitions of these quantities. Like now meter, or at least I think that a meter is on the verge of being redefined by the SI. It's like coming up in their next meeting in 2019, I think it is. That it's going to become the distance that something travels. Or maybe it's kilogram. Kilogram or meter, one of them already changed, the other one's about to change. But
Meters
essentially we're,
light in a fraction of a second.
yeah, so the meter changed, the kilogram is about to change. It hasn't changed yet, technically. But the idea is we change these definitions for a reason. We come up with a better description of them. And there's a certain amount of circularity to that. Like, we change what the definition is, and then we measure stuff, and then we change the definition again, which is kind of like, how are you making any sort of progress there? Are you just sort of like shuffling the chairs on the deck of the Titanic, as they say? But in fact, we seem to make progress, right? Even though we're redefining these fundamental quantities that we're supposedly measuring. So it's something the conventionalists wanted to just make static, like temperature is this, never changes. But in fact, historically, we do change it.
I was gonna say, it sounds as though measurement in its entirety is basically, it's based upon human activity. It's not based upon, for example, we're in thermodynamics, you have certain properties of a material that are intrinsic to that particular material. And so the measurement, you can never say that measurement is a property of an object. A measurement is relative to the individual. I can measure this as 6 fingers long or whatever, 2 fingers of whiskey,
Right.
which is not the same.
It's all your interaction with the object.
Correct.
And so, you know, I think that we all have a common way of describing that encounter with these objects, and we come up with ways of describing how that works. And it seems to be somewhat objective, right? But there is a subjective element to it as well. We experience it slightly differently, but similarities emerge.
Right, that's the whole point of measurement, is that we are agreeing that we're going to measure out there's certain things by this standard, which is the whole point of SI, System International.
Yeah, I think it helps us communicate, right? I think that,
It's like a language.
right,
It's like a language.
yeah. That really reminds me of. I was just gonna say this quickly, and then I'm gonna move on. You said it's like a language, which is a really cool statement. You know that one of my favorite philosophical psychoanalytic theorists, Jacques Lacan, said the unconscious is structured like a language. And that was like one of his fundamental observations, and one of the reasons why he's very famous. It's really interesting you just said that about measurement theory, but I think it's true. Why we measure, how we construct these models of the world, it allows us to communicate with each other in a common way that meaning can be conveyed still. It's cool.
We should consider an alternative career whenever it's out.
There you go. Or, you could just be a philosophical engineer. So, history teaching us is a thing. And so Thomas Kuhn, pretty famous, he wrote a book called The Structure of Scientific Revolutions. I don't know, some of you may have seen that book around. It's a pretty famous one. He and others pointed out that the idea that the hypothesize, then measure, then interpret, then judge scientific method that you guys probably have been assaulted with since you were young is rarely actual for significant scientific progress. So like when something really big happens in science, it's almost never because somebody was like, here is a hypothesis, and let's set up an experiment to measure it, and then let's interpret the results, and then make a judgment about the hypothesis. That is almost rarely, it's rarely the actual case. Instead, we refine our measurements to the point that they expose a lack in our theory, and that's kind of when things start to shift. the lack in our theory then becomes the focus. Like, for instance, you guys remember a couple years ago when somebody claimed that they measured the speed of light to be faster than the speed of light?
What?
No.
Yeah.
Are you talking about like our measured?
Yeah, there was a
measured it at?
there was a lab that like they were getting consistent measurements of the speed of light, like in a certain context, to be faster than what we think the speed of light in a vacuum is. Like so, and according to the theory of relativity, one of the I think it's the special theory of relativity, that nothing can move faster than the speed of light in a vacuum. So that made a lot of ripples in the science world, and so everybody comes out with an opinion right away on it, like, no, can't be the case, and then other people are like, yeah, I mean, why not? Why couldn't it be the case? Like, it's just a theory, and we know it's not consistent with quantum mechanics, so something's got to be wrong somewhere. And in any case, it probably, I think that, I don't know how long it took them to come back with the retraction, but essentially it was a measurement error that they had.
Nice.
Yeah.
I forgot to add the 4 and divide by the 2.
It's so, like, I mean, you gotta feel really bad for those folks. Like, I mean, I'm sure that they like double checked, triple checked. Before you come out with something like that, you gotta make sure you checked everything. And I'm sure they did. And it was probably just something that was too subtle for them to pick up on. And so, but once somebody makes a claim that the theory is broken, all of the measurement starts to focus on that, right? And it looks for that seam, that crack in the theory, and it focuses on that and refine the measurement more and more until the theory is exposed more and more to be broken, how it's broken, etc. And then, finally, a new theory emerges that can explain the lack in the previous theory, and that becomes the new theory, and then until we find the crack in that one, and then we gotta focus in on that. So that's how science really seems to progress in significant ways. Surely this process of hypothesize, measure, interpret, judge is like a daily process for scientists and for engineers who are doing any sort of research. But even engineers doing any sort of design, when you're testing prototypes, you're using this all the time. It's not that this is invalid. It's totally valid. It's just not how large shifts in science happen.
Not how major breakthroughs happen.
That's right. And Kuhn's is about like scientific revolutions and stuff. So it's not how revolutions happen. Okay, now I had a really good time naming this one. Bliss is ignorance. Finally, we call into question the very idea that a real value even makes sense without a certain amount of useful pretending. What does it mean to say, measure the speed of light in a medium? We must, of course, assume and try to control certain aspects of the medium that we know are never completely the case, such as that it has uniform properties like density, temperature, and pressure. We all know that real materials have variations in them. So even when you're trying to measure something like the speed of light in a certain medium, you have to make these sort of assumptions about uniformity that aren't ever actually the case. Assumptions about the temperature being uniform, the pressure being uniform, that are never actually the case. So even the idea that there's like this real quantity of like speed of light in a certain medium, it doesn't really hold water even when we just think about it, like, what does that even really mean? We're making all these simplifying assumptions that never actually happen. Moreover, we're assuming a completely static, repeatable measurement environment, while we all know perfectly well that one cannot step into the same stream, twice step into the same stream. Sorry to ruin that quote for you. Cannot step twice into the same stream. So that idea that nothing is ever the same, everything is always changing, we know that that's the case, but in order to make sense of things, we make these simplifying assumptions, which is fine, but we should just recognize that we're doing that, and that realism is a really useful approximation of reality, I think. That's the way I understand it. So these suggest, you don't need the S on the end of that. These suggest a new understanding of the relationship between measurement and theory. So here's a new paradigm that I'm going to just present that hopefully will help make some sense of this. So these critiques of realism lead us to an emerging model-based paradigm in the epistemology of measurement. This view understands the limitations, circularity, and ideality of measurement, yet forges a new path ahead. We might summarize this view as advocating something like the following attitude toward the epistemology of measurement. So I like centering them around the concepts of accuracy and precision. So the accuracy of a measurement has been defined in the past as its nearness to the unknowable real value. Now we're going to redefine it to be its agreement with values reasonably attributable or attributed to a quantity given available empirical data and background knowledge. So if it's accurate as a measurement, that means that it's close to the value that we can reasonably attribute to the real value. It doesn't posit that there's some real value to be had, but it's reasonable. But we could be wrong. It's accurate to the given state of our knowledge now.
It's close enough.
Yeah, and that's recognizing the fact that we might not know. Some major thing might be wrong with our model for what's going on, but as well as we can measure it, that's what accurate means. And then precision of a measurement has in the past been defined as the size of its clustering. For example, in terms of statistics, it's standard deviation, right? Now we define it to be a type of inaccuracy, so tying it back to accuracy. So a type of inaccuracy from uncontrolled variations of indications. So precision in the past has been, people love using the dartboard as the illustrative device. So if you're accurate, you would be close to the bullseye, but you might be spread around the bullseye, but your mean value is near the bullseye. If you're precise, that means you're clustered tightly, but you might not be accurate. You could be over here somewhere. So this new way of thinking about accuracy and precision gives you kind of an idea of this model-based epistemology. On a higher level, we develop models and measure and refine the models and measure some more. That is, measurement refines theory and theory refines measurement. So we just recognize and acknowledge that it's sort of circular, like we are working on refining our theory by measuring, and we're also working on refining our measurements by theory, and they go together and they complement each other. Measurement processes inform theoretical models through which measurement results are interpreted. The interpretation refines the model that informs the next generation of measurement processes, etc. And then just for fun, embrace the circle as it embraces you. Yes?
So, just on a random question, I guess,
Yeah.
have they ever tried to make the standard of measurement strictly theoretical?
So, yes. I think that is roughly what the SI is trying to convert over to doing. They're trying to say, well, we're going to find length to be, or we're going to find a meter to be measured by this length that we can specify completely theoretically, and then we can measure more and more accurately. But I think that, and I think that, potentially we're going to come up with static concepts like, length will be defined a certain way, a unit of time in a certain way. But I think that our recognition that a lot of times our measurements actually make us change our theory from a historical point of view is good to recognize. And so it might not be the final definition, but it's like for now, that's our definition. And we're going to measure some more and see. Maybe the theory needs refined eventually. Yeah.
Would the speed of light be a theoretical or more concrete measure?
Well, so the speed of light, so for now, the idea is the speed of light in a vacuum is a constant, and it cannot be exceeded. And so that theory looks pretty good right now. But we'll see. I mean, maybe some lab will come out and they'll be ridiculed again for having measured the speed of light to be faster than what is known as the speed of light in a vacuum. But maybe they'll be right. Maybe there's a certain crack in that theory. Right now, it is certainly the case that quantum mechanics and relativity have not been sewn together in a consistent way. And string theory is supposed to help us get there, but as far as I can tell, not being up on all of the latest research, but I feel like I would have heard, we haven't figured out how they're consistent at certain scales. So.
Because I was going to ask, because Matt mentioned that if everything is based on theory, it's kind of an odd saying that we're basing our theory on something that's concrete, which we did measure, which is not theoretical. Because the speed of light was measured at some point, and so we're stating that as a observable fact for now.
Mm-hmm.
So as soon as that is shattered, assuming that maybe someday it will be, then all of our definitions have to be readjusted. So I'm kind of wrestling with this. If we're trying to get if the SI unit system is trying to get everything based on the speed of light, which is a concrete measurement, that's creating everything in theory.
Right.
That's actually making everything measurable and in concrete, not based upon theory.
Yeah.
So kind of like if we're trying to make everything more theoretical, it's kind of an odd saying to say that because our basis for it is measurable, concrete.
Right. I think that we're seeing that circle, and what I'm saying people are claiming, and I think that it is not unreasonable to say, that it seems like we still make progress even though it seems circular. Like you're saying, like the theory is based on a measurement which is based on the theory. How does that work? And it's not totally clear, I don't think, how that works. I think that part of what I'm trying to show is that it's messy in reality and it's not quite clear, but somehow it seems like we are progressing, even though there is no clear foundation for all of this in some sort of objective way of looking at it. It seems to be that theory moves ahead with measurement hand in hand, and somehow that works. Or maybe we're just fooling ourselves and it doesn't work, but it seems to work.
It's like building a tower. You need one thing to build on top of the next. So I mean, in that regard, it's not like a difficult thing for me to comprehend. It's just more of the circle seems to be going up. So
Right.
The speed of light measuring 3 times 10 to the 8 is a measurement, but the idea that you can't surpass it is theoretical. So in nature, the speed of light is theoretical. It's not measurable.
Yeah, I think that the idea that the speed of light in a vacuum is a constant that doesn't change for any situation. Well, gravity, and so
that could mess up light too.
gravity is a really interesting idea. I don't want to even. I am not prepared to speak on gravity and time and their relationship. But let me just say that some really interesting movies lately have discussed this theme. And if you change if you change the gravitational field you're in, time is different for you. So that sounds very fiction-y, not even science fiction-y, even to us, and we know it's true. So, in any case, that's fine.
How do you go about changing gravity?
You gotta go to a different planet, mostly.
What is gravity? We don't know, right?
Well, at least now we know.
Oh
that
my
it's
God.
It's a big field.
Stop. But also, gravity is like kind of an illusion in a way, the way that we understand it. It's like it curves space, but we don't like to think. We're like all good Euclideans here, and we like thinking about space as being nice and flat, but it's not.
wibbly wobbly.
So yes, you guys are doing a good job of embracing the circle as it embraces you. So good job on that front. That was my interpretive line.
Actually, it is a circle.
Yes. In the right gravitational field, that would be a circle. Let's talk about signals and types of signals. So, I'll open this one.
Just stick down 4G metals and 2x.
Just escape from the molecular hypothesis.
There we are.